This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
There are multiple matching networks. In this particular case, I'm looking at L-based L networks. And if you're looking at these L networks in order to do, the matching, and an L network is just like you've got a shunt and a series element. You've also got pi networks, which I haven't gone through this in this course, but you can actually look it up and you can actually also see about pi network matching. But in this particular case, I'm talking to you about L networks. And I said if you're using an L network, there are two potential manifestations of this L network, and it was essentially if you've got the load, you can either have initially a series load or a shunt load, and then you've got the opposite. And what I was hopefully was able to convey to you all was I'm giving you a simple rule of when to use which one of these two I guess networks. Let me describe it that way. And the reason for that was, depending on which network you choose, there may or may not be a solution. But if you choose them the way that I've suggested, you are guaranteed to always have a solution, right? So that was the only point here, right? Because I've had a few questions about this point, so I'm just trying to emphasise to you. All I'm saying to you is, hey, you can if RL was greater than Z0, you can still use this, but there's a high probability that you won't be able to find an appropriate solution for it, right? You won't be able to find purely lossless elements that you can add that will give you a solution. Right, that was it. And likewise, if your the real component of your load impedance is less than Z0, if you chose this, well, you may get a solution, but you may not. But if you choose it based on these following rules, you're always guaranteed a solution. Okay. Now, the truth of the matter also is that yes, you'll always find a solution, but it might not also be the best solution. And we'll talk a little bit about what best solutions are in one of the later examples, which we're going to talk about today. Okay, and I just provided a reference for all of you to go look at POSAR in order to see the derivation of the mathematics, in order to see how that, why sometimes there is a solution, sometimes there isn't a solution. Okay. Then I went through the process of giving you some rules of thumb or some, I guess, mechanistic ways of being able to do matching using the Smith chart. All right, and I went through and wrote down, a set of rules in order to be able to do this. And I said, well, we always start with the impedance or admittance Smith charts. And I also suggested that we always move from the load, or we start at the load and move towards the generator, just in order to stop any confusion. And then I mentioned that our aim is always to move on constant R or constant G, so constant resistance or constant conductance circles. And I talked about it briefly, but I just wanted to re-emphasize the reason why we're doing that is because we are building lossless networks, or we're trying to build lossless networks, so therefore we're only playing with admittances, imaginary components of the how do you call it, we're only adding some of the imaginary components, so we're adding only susceptances or one-on susceptances. And then I just said to you how to recognize if you're adding, if you're moving in a particular direction on an R circle or a G circle, if you're on a shunt or a series or on shunt, and essentially to be able to identify if you're adding, for example, inductance or capacitance, right? And it's obvious which one it is if you're in the Z chart. It gets a little bit more, sorry, if you're dealing with impedances, it's obvious when you're dealing with admittances, it gets a little bit more complex and it can be confusing. That's why I just put those 2 points down there, so therefore it can actually remind you so that you can be aware, what am I actually doing? Okay, so then we went through a simple example, which you've got the notes, we won't go through this one again. But what I was going to do was look at a single stub matching example. Okay, because this is one of the ones that I've had some questions. So okay. So essentially what we've got here is we're trying to match an impedance or an admittance, and essentially what I've said is we were going to either add, and this is still a ZL, sorry, or a YL, it doesn't really matter, but it's a ZL. What I'm saying is now that we're going to be using transmission lines instead of lumped elements in order to do our matching. And specifically, what we're aiming to do here is to determine two things. One is if we've got a load, what distance, and then at what distance do we need to add a shunt load, a shunt stub, in order to match, right? And when we went through the process of describing was we can have a shunt stub which is either open or short, right? And then we can also have the series stub, which can of course be open and short. So let's go through this following example. And I've brought my very dangerous piece of equipment again, so let's go. Okay, so let's go through this example. So what we want to design is a shunt stub, right? And I am asking you to design two single shunt tuning networks to match this load at 50 ohms. All right, and what I should have also probably said is that the shunts themselves are open circuit rather than short circuit stuff. So I should say design two single OC shunt tuning networks to match this load to 50 ohms. All right, so essentially what I'm asking is let's design two of these networks in order to do the appropriate matching. Now, what you'll find is that when you're going through this process, that you'll find that there's naturally two, two solutions. In most cases, there are two solutions. But there's going to be, what the aim here was to also go through the process of explaining to you that even though you might have two solutions that give you a match, one may be better than the other for some reason, or for some reasons. Okay, so can someone tell me what they think step number one is? I mean, you've also got them on page 11 in the notes, but it'd be nice, rather than just reading it out, if someone can say to me, step number one is this and for this reason, so then we can start the process. Step number one, what is it? Normalize. Okay, so we normalize, right? So we had 15 plus 10J, we normalized it. What do we normalize by?
50.
Is it always 50?
No.
When, why, okay, so, okay, should have said yes, and we normalized it to 50 in this particular case because, I guess what I should have put in the question is, we want to get to 50 ohms, or if we were using the characteristic, a line of characteristic impedance of 50 ohms, right? So there's probably, I think we want to match it to 50 ohms. That's sufficient to say to you that you should be normalizing it to 50. Okay, good. All right, so we've got that. We've got the normalized value. Then what? So it's probably between step one and step two. Oh, yeah. So we've normalized it, and then what do? We plot it. Okay. Can someone, I mean, I've got it here, but can someone tell me how do you read a Smith chart? How do you find this point? So I've said the point is 0.3 plus 0.2j. How do you find it? Okay, so what we want is we want to find, we look along the, what I refer to as the real axis, and we find the point 0.3, and then what we'll do is we will find 0.3 plus positive 0.2j, right? So if we look at these lines, at these curves, we can see that this curve here, right, that dark curve here is 0.2. If I ask 0.3, where would 0.3 be? 0.3 plus 0.3. Where would you find it? Sorry? Sorry, I'm a bit. Remember, I'm old, right? I'm twice your age, so you got to be loud. Yes.
Is that 0.3 plus 0.3?
Yeah,
So
it'll be just here. All right. Okay. Sorry. Yeah. Sorry, my. And if I said 0.3 minus 1.2, where would it be? Yes. Okay, so you find the imaginary bit here, minus 1.2.
It's about 6 o'clock.
Okay, all right, so 0.3, we said the 0.3 lines here, all right, because we're looking at 0.3, and then we have to find negative 0.12, it would have been there, okay? It's got nothing to do with the question, I'm just trying to make sure that you can actually find all these locations on the Smith chart. Fantastic. Okay, so the next thing we need to do is what? Draw that?
Draw the circle with the radius of the impedance.
Sure. Okay. What does that circle correspond to?
All the impedance with the length of the transmission line.
Okay, so if you connected a transmission line to that impedance, that's all the impedances that you would see at the end, as you were going through the length of transmission line. Okay, good. And it also kind of corresponds to the voltage. When you draw the radius also corresponds to the voltage standing wave ratio of that particular system, right? So in this particular case, if we wanted to work out voltage standing wave ratio, so the way that we would do it is, essentially this, you draw it, okay, so that tells you all the impedances, and if you wanted to work out voltage standing wave ratio, I said just grab it from there, go down here, read off the voltage standing wave ratio. Okay, excellent. So we then drew the voltage standing wave ratio curve. Okay. Then, what do I do? Okay, I'll put this next to each other. Okay, what do I do next and why? We're going to use Smith charts a lot, especially when we're doing transistor design and things like that. That's why I'm overemphasizing this today, so therefore you've got the solid foundation. Okay, what do you do next? I've drawn this other circle. What is this other circle? What does this other circle correspond to? What does that mean? Yes. Yeah. Yes. Yes. But what does that mean?
As we want to match impedance to the origin point, so we have to move along a equal conductance circle. So we plot the point intersection of the voltage standing wave ratio circle.
Okay. Yeah. Good. No. Good attempt. Good attempt. Okay. All right. Good. Okay. So essentially, what we want to do is to work out. Remember, we've only got complex. We're building a lossless network, so we've only got complex elements that we can deal with, even if it's a transmission line. It's complex. Oh, sorry, it's only going to add to the complex component. It's not going to add to the real component, right? So what we want to do is we want to identify, you know, points on this, points where, which will then all the potential points. So the circle 1 plus JB identifies to us all the potential points which if we're on, and if it's an impedance, it gives us a resistance which is on that circle, or which is on the Z equals 1 plus JB circle. Or if we're in impedance and we're going to admittance, it also identifies those points, right? So essentially, it's identifying all the points which will get us to 1 plus JB on the real or imaginary in terms of impedance or in terms of admittance, right? That's what it's doing, and you're right. It's the Y equals 1 plus JB, which is also identifying to us all the elements which have that particular admittance, which have which only change in terms of which have got a constant real part of 1, but have got a varying admittance value. Okay, so what we do in this particular case, we want to work out what's this distance from the load, right? That we once we add a shunt element will match to 50 ohms. So what we do is we draw these two circles and then we look at the intersection. All right, and essentially what this is saying is, as we're moving along this line, we're moving on this VSWR circle. But what we're able to do is it's also highlighting to us that there are 2 points where we've got, if we map the impedance to an admittance, it leads us, or the impedance to an admittance, it leads us onto this particular circle, which allows us to match it using just a complex element. Right? So the next thing that we do is, as your colleague has just correctly pointed out, we draw the Y plus JB circle, right? Which was essentially you work out the the radius of the Z plus 1B circle, circle of Z equals 1 plus JB, and then you just move it across, put it in the center, and you draw that circle. Now, we now have identified the potential 2 locations where it's possible to have a match. Right? Now, we know that these are impedances, right? Because here we were adding, it was an impedance plus an impedance. This is just an impedance that we've added, right? Which also tells us that essentially we've got a length of line this much or a length of line this much, which will get us to a location where we can then, when we convert to admittance, we can add a complex bit and it will cancel out and we'll get a perfect match. Now, how do we identify what length of line the value of D? We said we're at this particular location and we've got 2 solutions, right? One solution is, we've got many solutions. Let me say the following. We've got multiple solutions, but the 2 smallest, sorry, the solutions that have got the shortest, the 2 solutions that have got the shortest length are the two points that I've drawn on here. Can someone tell me why that's the case? You can go many times around the circle. Absolutely, yes. Okay, so we start at this point. We want to move to that point. We work out essentially, rather than me answering these questions, what do I do next? All right, I'm here and I want to get here. What length of line do I need to add? Okay.
What size?
Yeah, so what we do, in order to identify this, we say, okay, let's draw a line, and that gives us the location. We want to move a particular length of line to get to this point, so we draw, again, this particular line, and therefore we then read on the outer circle what length did we need to move towards the generator in order to be able to achieve this point, or achieve this impedance. Okay. How about here? What do I need to do? How do I calculate this one? So, right. Why can't I go anti-clockwise?
Not going to the generator.
Right. And I can't be producing negative lengths of cable. Right. No, but it's important. I'm just making sure everyone's aware of why you're doing this. Okay. Perfect. So then we've got D1, we've got D2, right? So we work out the distance in length here, right? And it's in terms of wavelength, right? Okay, that's important because it's all relative to a wavelength, right? So here what we're saying is distance 1 minus distance 2, it's 0.7 minus 0.34 is, or it's 0.78 minus 0.34, it's 0.44 is the distance. 0.44 L, or 0.44 lambda, right? It's giving us the answer in terms of a wavelength. Why is that important? Well, if we change the wavelength, the actual physical length of line will change, and in this particular problem, what we'll do is I'm going to go through and show you how you can quantify that one solution is better than the other, because we'll find two solutions, and then what we'll see is how well do they match at different frequencies, right? Because even though you've got a match, you're only determining this match, in this particular case, for a specific frequency. It's not giving you necessarily a broadband match. What does that mean? Or for a large band of frequencies, right? Whereas it's only matching at one frequency, right? All the work that we're doing here, we're actually matching the circuit using this technique at a particular frequency. So we're getting a perfect match at a particular frequency. As we deviate from that frequency, what we'll see is the match gets worse, worse, and worse, right? Okay. All right, so we've gotten this point, we've worked out what the length D1 is, we know what the length D2 is, right? So we're now at either this location, right? Because remember, we want to add admittances. This is an impedance, this is an impedance. How do we work out admittances from impedances on the Smith chart? Yeah. So we go through on the circle. What we do that we've drawn, what we do is we go through the origin, and it's the point diametrically opposite which actually hits that point, which actually, and the impedance is the point at which it hits that voltage wave, the VSWR circle that is diametrically opposite to the impedance point. So impedance, admittance, impedance, admittance. If this was impedance, where would the admittance point be? It would be that, right? So you're just flipping through the origin, right? It's just on the opposite. Okay, perfect. All right. So now we've got the two shunt elements that we need to add, right? So we've got one that is, we need to add, essentially, we're down here, so we need to add positive, so this is negative 1.33, so we've got to add positive 1.33, and the other one is negative sorry, is positive 1.33, so we're going to add negative 1.33 to cancel that out to be here. Right. How do we determine what the length of those stubs is going to be? We've got an open circuit stub that we're going to add. How are we going to add it? How do we know what length it's going to be? And what's the process that we need to follow? Well, essentially, what's the admittance of an open circuit stub? Zero. What's the impedance of a short circuit stub? Not admittance, impedance. Zero. Okay, good. All right, excellent. All right, so depending, you either start, depending if it's a short or an open circuit, and depending if it's admittance or resistance, you choose the appropriate point where you start. Okay, we're looking at admittances, right? And we said the admittance is of an open circuit stub is 0, and we want to add positive 1.33 ohms. How do we find out what the length is? Okay, so we know this is the admittance of 0, and essentially what we do is we travel, depending on the length, we're travelling on the Smith chart, right? So we want to get to positive 1.33, that point, right? So since we started from 0 and this is the length, you just read it off, and it's point, I don't know, I'm a bit blind, 0.4 something, 0.47, 0.48, right? So that's probably 0.147 is probably the right value. Okay, so now what we've done is, if we're at this location and we add a shunt of length of 0.147 lambda, hey, bingo, right? We are now matched. Perfect. Okay, what happens if we were in this location? Well, we've got to add minus 0.133 J. How do we work out how do we do that? Somebody? Okay, so we know if we're at this location it's positive, so let's continue around the circle, right? Around the Smith charts. And as the length of the open stub increases in length, right, it goes from 0, it hits, 1, 1.3, 1.8, 2, 3, blah, 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 infinity, 50, 20, 10J, minus 5J, minus 4J, minus 3J, minus 2J, minus 1.6J, minus 1.4J, 1.33J, minus 1.33J. Right? So therefore the length of stub is essentially, we start at this point and we just choose it to have the following length, which is point, who can read this for me? Wait a second, I always get this one. 0.25, 7, 31, 33, 24, 3, 4 something, or 3, 5 something. Okay? Okay. That's the length of the stub that you need to add, right? Because you want minus 1.33. So it's from here all the way around to that location, and we read the length, and it's that's minus 0.13, and that's 0.353 lambda, right? And if you add minus 1.33 J to this, you get back to the origin. Is that clear, or is it? Who's it not clear to? Because I mean, this is so vital. I just want to make sure that you're all. It's all good? All right. Okay. Now, we've identified that we've got two solutions, right? We said that the two solutions were as follows, right? We said, well, we had the same impedance, and we could either add, if we looked at this, two lengths of line here, which gave us a solution. There was one here and one that was all the way across. These are our two solutions. And likewise, you know, the two open circuit stubs. One, in order to match this one, it was 0.147 lambda, and this one was 0.53 lambda, sorry. Okay. Okay, so therefore, once we've got those matched, gamma in is equal to what? If you've got a perfectly matched source, or perfectly matched network. Zero, perfect. No reflection coefficient. Now, what I'm going to, you know, let's for argument's sake say that I asked you to design this circuit for 2 gigahertz, right? What do you need to do now? Do I interchange anything, or what do I need to do to make it matched for 2 gigahertz? Okay, we started the conversation off where I said, I was talking about wavelengths, right? So therefore, when you're determining the length of the stub, or the length of the D, that's where the frequency of operation comes in, right? So when I said we're matching this at 0.44 lambda, what's lambda in free space at 2 gig? How would you work it out? Wavelength. How do we work out wavelength in free space? Yeah. C equals FL. So L equals C divided by F, right? So you can work out what the length is. Okay, so now you've worked out the length. So you can work out the length that you've of line you've got to add here, and the length of the stub. And likewise, you can do the same, you know, for this circuit, right? Where you've got a different length and a different length of stub, right? Now, as engineers, usually we don't want to do. We want to be able to compare which one's better, right? Because there might be multiple solutions. Now, if you're looking at a single frequency, we know both of them are perfectly matched, right? That's how we design them. Maybe one of the things that could be interesting in order to be able to say if one is better than the other is to say, well, suppose I was looking at over a frequency band, which one gives me better performance? Okay. So essentially, how would you do that? What is the process that you would follow in order to work out what how good a match have you achieved? Okay, so what we would do is we would start putting in all the numbers that we've calculated, but then move or determine what happens at a different frequency. As an example, okay, let's grab this circuit, right? And we've said, we've designed it now. What's happened is I've given you a box of coaxial cable, or a box, of the air-filled coaxial cable. I said, oh, we want to design it for 2 gigahertz. So you got the big scissors out, or the big pliers. You cut the wire, right? And you built me the network. And then I said to you, hey, how does it work at 1 gigahertz? You can measure it, or you can actually try to calculate it. And that's what I'm asking you to do. And essentially, all we're doing is going through this process where if we've got a particular length at 2 gigahertz, if it's, for example, if it's, if the length is 0.5 lambda at 1 gigahertz, right, or sorry, at 2 gigahertz, what length is it? L equals L at 1 gigahertz. How, in terms of wavelength, how long is it at 2 gigahertz? How many wavelengths?
1.5
Not 1.5.
I see the less is 1.5 the wavelength.
No, it's okay. So it's 0.5, right? So 2 gigahertz. Okay, 2 gigahertz is 0.5 lambda. All right, and it's just think of it by lambda. I'm saying you've calculated it at 2 gigahertz. You've actually cut that wire at at that particular wavelength, right? Now, if you're half the wavelength, if you're half the frequency, the wavelength is doubled, right? So that's equivalent to 1 lambda at 1 gigahertz, right? No, I've got it the wrong way around. 0.25 lambda at 1 gigahertz, and yeah, I've got it the wrong way around. I apologise. Okay, no, just in this calculation. So what I'm just saying is, what's happening that's different is all of a sudden now, because you're at a different frequency, that piece of wire is no longer 1 lambda. It's half a lambda, right? And if you were at 4 gigahertz, it would be 2 lambda, right? That's all I'm saying, right? Nothing special, nothing magical. Just, you've now think of it as, I told you to design it, I gave you the box of coaxial cable, you cut the coaxial cable, you made the circuit. That is now a fixed length, right? And then that's now when we're changing the frequency, essentially what we're doing is we're changing the effective wavelength. So essentially, all I was asking you to do in this particular example is, okay, so you start off with a particular impedance, right? And then we add, for example, 0.44 lambda. If that's a particular value at 2 gigahertz, at 1 gigahertz, it's the equivalent of 0.88 lambda, right? So therefore, you find the point and you move across in order to find, the effective length. Right, and then what happens is you then add, you find the admittance, and then you also, the length of that wire now is longer or shorter depending on the wavelength. And then in order to work out how well you've actually matched that solution, you find your ZL now, and you then draw your VSW circle. Right, and if you do all that, what you find is solution 1, right, because we've got 2 solutions, remember? We calculated, if you go through the process and you recalculate everything for the Smith, from the Smith chart, rather than going, for example, if you were at 2 gigahertz, you were 0.387 lambda. At 1 gigahertz, you're at 0.7387 times 2, right? I can't do the calculation in my head at the moment. So essentially what you do is you go through the same process, but in reverse. And then what happens is, if you work out your solution for 1 gigahertz, you find that your reflection coefficient is 0.48. Right, at 2 gigahertz it was, what was it at 2 gigahertz again? We built a matching network for 2 gigahertz, so the impedance so the reflection coefficient was 0, right? But at 1 gigahertz, if you go through the calculation, it's 0.48 for solution 1. For solution 2, because it's a much larger length of line, and if you go through the calculation, your gamma is 0.85. So it's much more poorly matched, right? So therefore, if you were building your system to operate from 2 gigahertz down to 1 gigahertz, you'd choose solution 1 over solution 2, right? As an example, because it's got better matching in the frequencies of operation that you want. And generally, as a general rule of thumb, as your length of transmission line becomes larger, your match over frequency gets worse, right? Because it's now a larger number of wavelengths incorrect. Right? So therefore, usually you try to build everything with the smallest lengths of coaxial cable or whatever when you're doing these matching networks. Exciting? Well, at the very least, you can design a matching network now, right? So you should be pretty happy. Yes?
How about the previous method when matching the reactance, the impedance and the capacitance? Because we doesn't include the length of the...
You mean the previous example where we added just J omega C? That's different. You don't have to worry about that. But you still now have to worry about the omega C's, because omega C at 2 gigahertz is going to be, at 1 gigahertz is going to be half of what it was at 2 gigahertz, right? So you still have the mismatch, right? So, and this is where most of our life as engineers becomes problematic, right? Because we design these networks and we want to match them so that we can get maximum power transfer and do all these great things, but nature's never that kind. So, and more than that, initially, when I was growing up, you know, if you got a modem that was able to transmit, you know, 1200 bits per second, you were king. Whereas now you guys want, you know, at least 100 megabits per second, right, over your coaxial cable, right? So therefore, you've got at least 50 megahertz of bandwidth, and you're going higher and higher and higher, right? So therefore, these problems become much more challenging because now you've got to match over 50, 100 megahertz, a gigahertz, multiple gigahertz, right? So therefore, generally what you do when you're doing this type of design is you try to match it in the middle of the band, and then you kind of hope that, hey, it's not that bad at the edges. Or what you do is you don't look at an L-band match, you look at a pi or something else which gives you higher order so that you can actually start doing, you know, better matching over more of the band. But all of a sudden it becomes much more complex to do the matching network, and it becomes impossible for me to try to convey it in a lecture, right? But this is just at least teaching you the fundamentals. Okay, so we've done some basic matching, and we've spent quite a bit of time on Smith charts and the like, so I think we should be pretty good to go, right? Everyone excited? But what I would suggest, I'd strongly suggest this, because the next part of the lecture, I'm going to start very briefly on S parameters. But the reason is, when we're moving on, and in the next lecture or two, we're going to start designing power amplifiers. If we had just given a transistor model and a transistor, it was biased at a particular point, we've got its S parameters. In order to do that design, you've got to be using Smith charts and designing matching networks, right? So therefore, this weekend, between waking up and going out in the evenings, spend a couple of hours on the Smith charts. It's going to be very worthwhile. Right? So, yeah. Anyway, okay. So let's start very briefly for the next few minutes that we've got available in the lecture to start talking about S parameters. Now, I understand that you guys haven't gone through S parameters before, or you have? In the workshop. You've done S parameters in the workshop. Okay, good. So this is good, right? So tell me about S parameters. Who can tell me about S parameters? You've done it. Who is the person teaching it in the workshop? Who is the tutor or the lecturer? You must be the tutor. Andrew, okay. So what did he teach you about S parameters?
My workshop session is
today. Okay. All right. So you're going to get a repeat. So, okay. So essentially, what happens is when you're operating at high frequencies, it's usually easier to deal with power waves, right, rather than to deal directly with voltage waves and the like. Now, what I'm going to do here is, even though I'm writing these, and they are technically, the same as voltages, what I'm assuming, and I didn't bring a pen, so I'll have to use this, is when I'm writing these, at least for here, I'm writing V on the square root of 50, or the square root of the characteristic impedance, right? So I've normalized it, so therefore when you square it, it's V squared on Z, which is V squared on Z, or V squared on R is power. Right. Cool. All right, so it allows us, S parameters allows us to characterize high frequency two-port networks. Who knows what a two-port network is? Who doesn't know what a two-port network is? Right, it's just, you can think of it as a black box and it's got two plugs in it. One on one side, one on the other. Two ports, that's it. Right, so you've got a two-port network. And essentially, it's connected up to something, and as a consequence of that, depending on how matched it is or unmatched it is, you've got a power wave going into this network. And remember, I've written it as V1 plus because it's really a voltage, but it's normalized. So, but just think of it as a power wave. You've got a power wave going in, or a voltage wave, and then you've got a voltage or power wave reflected from that network, right? And we've been talking about that. And likewise, on this part of the network, you've got an incident wave going in and a reflected wave coming out. Nothing special. Is there something wrong, or no? It's a. Oh, okay. Well, just my bad handwriting, I guess. Okay, so I've actually defined this two-port network in terms of these parameters called S parameters, which are scattering parameters, and I say, well, voltage 1, and you can think of it, and I've drawn this little network, whatever. So you've got this imaginary network, you've got some network in there, and essentially what I'm saying is there's a relationship between the incident voltage waves and the reflected voltage waves. And then the relationship is given by these parameters called scattering parameters, S parameters, right? So I've written the incident voltages as a linear relationship. So the reflected voltage, I should say, at port 1 has a linear relationship of the voltages going into port 1 and going into port 2. Right? So if you think about it, voltage 1 is going to be voltage 1 plus a reflected component plus voltage 2 plus a transmitted component of voltage 2. That's all I've done here, right? And likewise for 2, in this particular case, I've got it as this voltage 2 is a reflected component, S22V2, of this signal, plus the transmission component of V1. Right? Nothing special, just linear algebra. Right? So I've written the reflected coefficients as a function of the incident coefficients. Right? That's all I've done. Okay, now, just for everyone's benefit, I have to define these scattering coefficients. And these scattering coefficients, the way that I've defined them is, and how they're defined, I should say, and not that I've defined them, I'm copying how other people have done the definition of scattering parameters. This is just a standard definition of scattering parameters. It's the ratio of your, in this particular case, S11, is your ratio of V1 minus to V1 plus when V2 is equal to 0, right? And V2 equals to 0 is essentially what I'm saying is when the output port is matched with a matched load. And likewise, we go through and determine S21, which is the forward transmission coefficient, which is essentially V1 to the ratio of V1 plus to V2 minus, and it's essentially when we have a matched load. Okay. Likewise, we've got the reverse transmission coefficient defined as S12 and the reverse or the output reflection coefficient. Okay? So they're just the basic definition of scattering parameters, and some of the properties of scattering, one of the important properties of scattering parameters as it concerns to lossless networks is essentially the power going in has to equal the power going out. Right, so you've got conservation of power. So if you look at, in this particular case, you've got S11, right, S11 plus S21, right, is equal to 1. So therefore, essentially, the power going in is going to be the power that's reflected out and the power that gets transmitted to the other port. It's just conservation of energy, right? And I'm doing that for both ports. Okay. Now, as a couple of homework exercises, because we're pretty much out of time, what I wanted you to do is to, and I'll also do it during the next lecture, is calculate S11 and S21 for this very simple network. You've just got a load impedance, you've just got an impedance, and this is your two-port network, right? And I want you to work out what S11, S22, S12 and S21 are going to be. And because it's passive, you can immediately tell me that S11 is equal to S22, right? So therefore, the impedance looking into this port once this is matched is the same as the impedance looking into this port when that port's matched, right? So therefore, you've also got this extra bit of information. All right? So what I want you to do is to actually calculate it, and we'll go through it in the next lecture. And then hopefully Andrew's gone through it for you, so therefore you can actually do my job and tell me what I should be explaining. All right. All right. Cool. I haven't uploaded these. Oh. Yes, you're right. I was writing them before the lecture, and then I was writing them before the lecture, and then my pen ran out. You're going to laugh. My pen ran out, and then I started to write in red ink.
This means a function. So this is the admittance which is 1 plus UB.
Yes.
And when you move to this point and just shift it, I know why shift because maybe this is.
We want to add admittances, right?
Yes.
Okay, but remember, you're now on an impedance circle, right? So this is impedance.
Yes.
But now you want to add an admittance. You want to add an admittance, which you're going to be able to add a complex coefficient, right?
Yes.
So you want to intersect this circle to intersect with this, so therefore you're guaranteed to only need to add an imaginary component in order to match it.
So we must go to this.
No, but that's, you're doing that. Oh, sorry, I've got my notes there. Oh, here they are. Okay. You got a D.
Oh, yes.
Right, so I'm trying to work out what D is. Right, that's why I say to you, well, we're at this point, and then I said to you, well, I'm going to add some line, and then I also want to add some shunt. How can I do that? Well, if I'm adding line, I can only move along this circle, right?
Yes.
Okay, that's the only choice I got.
Oh, yes.
All right?
Yes.
If I'm going to add, this is going to add a shunt.
Yes.
Okay. But I want to be this. We know that if we're adding a shunt, it's only, and it's a lossless line. It's only going to be adding an imaginary component. That's the only thing you can add, right? It can either be in series and add, or it can be a shunt, right? In this particular case, I asked you to do a shunt.
Oh, yeah.
Okay. So you can move. So, and you want to map to this circle. Oh, sorry, you want to map to the. I apologise. You want to map to that circle.
Yeah.
You're right.
Yes.
And then I say to you, well, how can I map to that circle? Well, the only way that I can map to that circle is if I'm converting from impedance to admittance, is if the impedance falls on this circle, because when I go diametrically opposite, it'll be on this